Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the heart of a mystery that stretches across everything we know. It's a story about the invisible threads that hold the universe together and the silent pressure that pushes it apart. We're going to wander gently through the origins of dark matter and dark energy. Those unseen forces that shape galaxies, stretch space itself, and yet remain beyond our sight. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the cosmic dark together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. In the beginning of the 20th century, our understanding of gravity seemed almost complete. Newton's laws had guided sailors, built bridges, launched cannonballs, and explained the slow waltz of the planets. To most scientists, the universe itself seemed like a vast, eternal machine, steady and unchanging. But one man, soft-spoken with a wild halo of hair, was quietly reimagining everything. Albert Einstein was working alone in a small apartment in Bern, thinking not in terms of force, but of geometry. To him, gravity wasn't something that pulled, it was something that shaped. He imagined space and time as one continuous fabric, soft and pliable, like a sheet stretched under the weight of a planet. Where there is mass, there is a dent. Where there is a dent, things move not because they are pulled, but because they follow the curve. Planets orbit not by being tugged around the sun, but because the sun bends the stage beneath their feet. It was a beautiful thought, almost poetic in its simplicity. But for years, it was only a theory, waiting for the universe itself to answer. That answer came on a humid island off the coast of Africa, on the 29th of May, 1919. Two teams of astronomers, one in Brazil, one on the island of Principe, had set out to capture something subtle and extraordinary. The moon would pass in front of the sun, and in that brief darkness the blinding light would dim just enough to reveal the stars around it. If Einstein was right, their positions in the sky would shift ever so slightly, their light bent by the sun's gravity. Clouds rolled in, the rain came and went, and one of the astronomers, Arthur Eddington, sat beside his telescope, hand steady, changing photographic plates in the damp air. When the eclipse came, he barely looked up. He was too busy catching starlight. Weeks later, when he developed the plates, he saw what no one had ever seen before. The stars near the sun's edge weren't where they were supposed to be. Their light had curved just as Einstein had predicted. Space itself had bent. The headline in the New York Times declared, "Lights all askew in the heavens." And almost overnight, Einstein went from obscurity to fame. But behind that celebration was something deeper, a quiet revelation. If space could bend, perhaps it could also stretch. If gravity could shape the paths of stars, maybe on scales too large to imagine, it could shape the entire universe. The idea of a static, eternal cosmos began to tremble. The stage itself was alive, expanding, changing. Einstein wasn't entirely comfortable with this. In his equations, the natural solution wasn't a still universe, but a restless one, either expanding or contracting. It seemed absurd to him. The night sky looked so calm, the stars eternal. So he added a gentle correction to his math, a balancing term to hold the universe steady. He called it the cosmological constant. It acted like a quiet, invisible hand pressing against gravity's pull, keeping everything still. Years later, when Edwin Hubble stood at the Mount Wilson Observatory and measured the faint light of galaxies, he found something astonishing. The farther away a galaxy was, the faster it was receding from us. The universe wasn't sitting still at all. It was expanding. Einstein, when he heard the news, supposedly smiled and called the cosmological constant his greatest blunder. But the truth is that quiet, balancing term would return decades later, under a new name, with far greater importance than even he could have imagined. For now, imagine that moment. Eddington's photographs drying under a weak lamp, lines of starlight shifting by a fraction of a millimetre. A proof so small it could be measured with a ruler, yet big enough to change our understanding of everything. Gravity was no longer a force, but the poetry of space itself. The universe had revealed that it could bend, flex and move, not like a clock, but like a breathing organism. And if it could bend and move, what else could it do? Could it hide? Could it expand forever? Could it hold secrets not made of stars but of something darker? In the years that followed, others would take Einstein's equations and stretch them to their limits. They would find galaxies that moved too fast, stars that spun in defiance of physics, and light itself bent by invisible hands. The universe was whispering that most of what exists isn't what we can see. It would take decades of careful listening to begin to understand just how much was missing, and how much of it still holds us together. So tonight, as you lie there, picture that bending starlight from a century ago, the first glimpse of the universe's hidden hand. A moment when the cosmos stopped being a still picture and became something alive, stretching, curving, and humming softly in the dark. By the early 1930s, the echoes of Einstein's discovery were still spreading through the halls of astronomy. Space could bend, the universe could expand. Yet what filled that space still seemed simple enough. Stars, gas, dust, all bound together by gravity's quiet pull. No one imagined that most of the cosmos might be hiding. At the California Institute of Technology, a Swiss astronomer named Fritz Zwicky was staring at a patch of sky some 300 million light-years away. Through his telescope, the Coma cluster looked like a sprinkling of pearls adrift in black water, each one a galaxy in its own right. He wanted to weigh this enormous congregation to find out how much matter it held. The trick was to measure how fast the galaxies were moving. If gravity was the glue, their orbits should reveal the amount of glue required to keep them together. It was a simple expectation, but the results refused to cooperate. The galaxies were racing through the cluster at nearly 1,000 kilometers per second. With only the visible stars and gas providing gravity, the entire cluster should have torn itself apart long ago. The numbers didn't add up. Something invisible was holding it together, something heavy, something unseen. Zwicky gave this missing component a name, Dunkel Materie, dark matter. He didn't mean dark like shadow, but dark like unknown. It wasn't an exotic term at first, just a placeholder for an unsolved puzzle. But behind the numbers lay a whisper of something profound. The visible universe, all those suns and nebulae, might be only the frosting on a far larger invisible cake. Zwicky's colleagues were skeptical. He had a reputation for brilliance wrapped in barbed wire. Students and peers alike found him difficult, unpredictable, and occasionally offensive. He once called his rivals spherical bastards, meaning, as he put it, they were bastards no matter which way you looked at them. Yet beneath the sharpness, he was often right before anyone else dared to be. His calculation in Coma was clumsy by modern standards, but his instinct was extraordinary. He imagined the cluster not as a gentle family of galaxies, but as a swarm bound by hidden mass. The light we see, he realized, could not tell the full story. If you were to hold a handful of glitter in a dark room and throw it into the air, the sparkling pieces would move not by their own shine, but by the air currents you cannot see. The galaxies too were drifting on invisible tides. For decades, Zwicky's idea lingered at the edges of science. The war came and went. New telescopes rose above the atmosphere, turning their eyes to faint galaxies billions of light years away. Yet the mystery persisted. every time astronomers tried to measure the total mass of the universe, it seemed to come up short. The cosmic ledger refused to balance. In the 1950s, radio astronomers began to map clouds of hydrogen gas beyond the bright disks of galaxies. The outer regions were spinning too fast, their motions impossible to explain by the light alone. Still, few dared to say the words dark matter out loud. The term carried the scent of the unprovable, of ghosts in the equations. Then, in the 1970s, a quiet, patient scientist named Vera Rubin would return to Zwicky's forgotten puzzle and prove that he had glimpsed something real. But in Zwicky's time, all he could do was write, measure, and argue. His paper ended with a line that now feels almost prophetic. If this is confirmed, then we must be dealing with an entirely new kind of matter. When you picture him in that Caltech dome, pipe smoke curling in the dark, the hum of the equipment mixing with the faint tick of cooling metal, you can almost hear the universe holding its breath. He didn't know it then, but he had stumbled upon the first crack in our understanding of what the cosmos is made of. Astronomy would later discover that what we see, stars, planets, glowing nebulae, makes up only about 1/20th of all matter. The rest is that same invisible substance Zwicky had inferred, distributed through space like an unseen scaffold. Without it, galaxies would fly apart, the cosmic web would unravel, and the night sky would be a far emptier place. Even so, it would take another half-century for his insight to take root. For most astronomers of the mid-century, the idea of hidden mass seemed like superstition. But as new instruments arrived, radio dishes, infrared detectors, computers capable of simulating gravity's dance, the evidence began to pile up. Everywhere they looked, galaxies spun too fast, clusters bound too tightly. The invisible hand was undeniable. It's easy now to treat Zwicky's discovery as inevitable, but it wasn't. It came from one man's stubbornness, his refusal to smooth the rough edges of reality to fit expectation. Science often advances not by harmony, but by contradiction, by someone willing to say, the numbers disagree. When you think about it, there's something almost poetic in that. The first proof of the unseen didn't arrive through fancy instruments or elegant theories, but through an argument between what the eyes saw and what the equations whispered. We now know that dark matter makes up about 1/4 of everything in the cosmos. If the entire universe were a pie, all the atoms, all the stars and planets would be one small slice, while dark matter would be 5 times as much, shaping the crust beneath. And beyond that lies another ingredient even stranger: dark energy, the silent expansion that fills the rest. But that realization would come later. For now, in Zwicky's dim observatory, a seed had been planted. The Coma Cluster shimmered on the glass plates, every galaxy a point of light surrounded by darkness. He could measure the speeds, he could see the imbalance, but he could not touch the thing responsible. It was gravity without substance, a weight without form. If space could bend, as Einstein had shown, then perhaps it could also hide. Perhaps the universe had built its own scaffolding from something that neither emitted nor absorbed light. Matter that revealed itself only by its pull. That idea, once almost heretical, would later become the backbone of modern cosmology. But in that moment, it was just Zwicky, alone under the California night, daring to believe that the universe was heavier than it appeared. Far beyond his telescope, those distant galaxies continued their race, bound by invisible threads. Their light, stretched and redshifted across 300 million years, would one day reach us as faint whispers of the unseen. And though Zwicky could not yet name it fully, he had given the darkness a beginning, a quiet recognition that what we cannot see may still be the thing that holds everything together. By the time the world had recovered from war and stepped into the promise of the 20th century's middle decades, astronomy had changed. Telescopes were sharper, film was faster, and the universe itself seemed more restless than ever before. Yet Zwicky's dark matter remained little more than a strange rumour buried in technical papers. Most astronomers preferred the comfort of the visible, the neat spiral arms of galaxies, the glow of nebulae, the reliable arithmetic of starlight. They trusted what they could see, but light, as it would soon turn out, was not the whole story. Far from the loud circles of theory and rivalry, a quiet observer was beginning her own patient revolution. Vera Rubin didn't set out to challenge the universe. She just wanted to measure how galaxies move. She loved the sky as a child, not for its grandeur, but for its calm. It was a place that always seemed to keep its secrets politely. And perhaps that was why she was so well suited to listen to them. In the 1970s, Rubin and her collaborator Kent Ford built their nights around a simple question. How do spiral galaxies spin? The idea sounds innocent, even obvious. But at the time, no one had mapped it carefully. The expectation was straightforward. If most of the mass in a galaxy sits in its bright centre, then the stars near the edges should move more slowly, much like planets in our solar system. Mercury races around the Sun quickly because it's close. Neptune drifts slowly because it's far. By all logic, galaxies should behave the same way. Rubin and Ford pointed their telescope toward the graceful whirlpool of Andromeda, the nearest large galaxy beyond our own. Night after night they measured the Doppler shifts, the tiny changes in light that reveal motion, like the rise and fall of a siren passing on a distant road. They expected a gentle drop in speed as their measurements moved outward from the galactic core, but the line they plotted didn't fall. It stayed flat. The stars at the edges were moving just as fast as those near the centre. The galaxy was spinning as though it were a single solid disk. By all ordinary physics, that should have been impossible. If the stars were truly that fast, gravity alone couldn't keep them from flying into space. At first, Rubin suspected an error. Perhaps the telescope had drifted, or the calibration had slipped. But every recheck confirmed the same story. Andromeda's rotation curve, as it was called, refused to bend downward. She turned to other galaxies, same result. Dozens, then hundreds, each one defying expectation. The pattern was undeniable. Something massive, invisible, and all-encompassing was holding these galaxies together. Imagine watching a carousel in the dark. You can only see the painted horses where a flashlight passes, their colours appearing and vanishing as they turn. Yet you can tell from the rhythm of their motion that the whole structure must be solid beneath the shadow, a wooden platform that you can't see, but that you know is there. The galaxies were like that. Their visible stars were just the painted horses, and the hidden platform was dark matter. Rubin's results met resistance. The idea that most of a galaxy's mass might be invisible felt too strange, too untested. She was one of the few women in a field that often forgot to make room for her. Some observatories didn't even have women's bathrooms. She once had to walk across the dark grounds at night to find one in another building. Yet she stayed gentle in her insistence. She presented her data calmly, let the curves speak for themselves, and invited others to check. They did, and the universe agreed with her. Over time, her quiet persistence transformed skepticism into acceptance. It became clear that every spiral galaxy was surrounded by a halo of unseen mass, extending far beyond the reach of its luminous disk. These halos, composed of something unknown, were not just decorative, they were essential. Without them, the galaxies would tear themselves apart. The invisible was what kept the visible from unravelling. Rubin didn't claim to know what dark matter was, she only proved that it had to be there, but in doing so, she changed the cosmic balance sheet forever. Her rotation curves became a kind of fingerprint, the unmistakable signature of the universe's hidden skeleton. It is strange to think that something so silent could define the shape of everything we see. Yet that's what her work revealed. The elegant arms of spiral galaxies, the clustering of stars, even the formation of galaxies themselves, all owe their existence to an unseen mass, roughly 5 times greater than the ordinary matter we're made of. There is a beautiful irony in that. Rubin, who spent so much of her life unseen by her peers, discovered the invisible backbone of the cosmos. Her science, like her temperament, was steady and luminous without seeking attention. "There is no problem in science that can't be solved," she once said, "if you have the right attitude and keep trying." Her discovery also bridged Zwicky's neglected idea to a new generation. What had once been a strange claim from a difficult man became, through her grace and patience, one of the foundations of modern cosmology. Astronomers began to picture the universe as a vast web, galaxies suspended in halos of dark matter that stretch across unimaginable distances. The visible stars, for all their brilliance, are just the glittering frost upon invisible branches. Today we know that these halos form the scaffolding of the universe. They guided the first galaxies into being, pulled matter together from the featureless haze after the Big Bang, and continue to bind clusters and superclusters in their slow cosmic dance. Without them, there would be no Milky Way, no sun, no Earth to gaze back in wonder. As Rubin's papers spread through the scientific community, the mood shifted from disbelief to quiet awe. The universe, it seemed, was far more mysterious than we had dared to think. Light showed us where matter shines, but gravity showed us where it truly is. When you look up tonight, every point of light you see is surrounded by an ocean of the unseen. Those stars twinkling softly are not floating freely. They're cradled in halos of invisible mass, the same substance Rubin's careful eyes brought into view. The next time you trace the spiral of a galaxy in a photograph, imagine the silent hands that hold it together, the calm rhythm beneath the swirl. And somewhere in that rhythm you can still feel her presence, steady, determined, and patient. The woman who measured the impossible didn't shout her discovery. She simply listened to the quiet hum of the universe and wrote down what it told her. By the time Vera Rubin's rotation curves had persuaded the scientific world that dark matter was real, another kind of evidence had begun to emerge, one that came not from measuring how galaxies move, but how they bend light. The universe, it turns out, is full of mirrors made of gravity. More than half a century earlier, Einstein had predicted that mass could warp the space around it, changing the paths that light follows. When Arthur Eddington proved this during the solar eclipse of 1919, the effect seemed subtle, barely measurable near the edge of the sun. Einstein himself thought it would have little practical consequence. Stars simply weren't massive enough to act as natural telescopes. The idea that their combined gravity could focus light like a lens felt too fantastical. But the universe had surprises waiting. In the decades that followed, telescopes grew larger, their eyes sharpened by mirrors and cameras sensitive enough to see the faintest flickers from billions of light years away. Astronomers began to notice that some of the most distant objects in the sky, the strange point-like beacons known as quasars, were appearing in pairs. One of these was labelled Q0957 plus 561, a name that sounds more like a code than a star. At first it seemed ordinary enough, but when scientists studied its spectrum, the unique fingerprint of its light, they found something astonishing. The two quasars were identical in every detail, as though nature had made a perfect copy. The explanation was hidden between us and that distant object. A massive galaxy sat directly in the line of sight, its gravity so strong that it bent the quasar's light around it. To our telescopes, the deflected paths looked like two separate objects. We weren't seeing double. We were seeing light take two roads through curved space, arriving from slightly different directions. It was the first gravitational lens ever confirmed, and it transformed Einstein's thought experiment into a new window on the universe. Think of it like this: space itself can act as glass, curving and focusing light just as a raindrop does. When you peer through a droplet clinging to a window pane, the scene beyond twists and doubles, reflections sliding and stretching in silent motion. The universe does the same, but on a scale so vast it defies imagination. Whole galaxies can behave like magnifying droplets, bending and amplifying the light of objects that lie billions of light years behind them. Fritz Zwicky had suspected this decades earlier. If clusters of galaxies contained as much dark matter as he calculated, their combined gravity would make them powerful lenses. But in his time, no instrument could detect such subtle distortions. It wasn't until the 1970s, with improved optics and photographic plates, that astronomers began to see what he had only imagined. Arcs and halos of light curling around clusters like ghostly rings. The discovery of the double quasar in 1979 was just the beginning. Soon, telescopes around the world and in orbit began finding these cosmic mirages everywhere. Some were simple doubles, others formed crosses or even full rings, where the background galaxy's light had been wrapped into a perfect circle, a so-called Einstein ring. These were not artistic tricks of perspective, but genuine echoes of space-time itself bending under the weight of mass. Every lens became a measuring stick. By studying how much a background galaxy was distorted, astronomers could calculate the total mass of the object doing the bending. And every time they did, the verdict was the same. The visible stars and gas accounted for only a fraction of what was needed. Something unseen was providing most of the gravity. Dark matter wasn't just inferred from the motions of galaxies, now it was drawn directly on the sky in arcs of light. Some of the most beautiful of these gravitational masterpieces were found in clusters of galaxies, the largest bound structures in the cosmos. Imagine looking through a magnifying glass at a city skyline at night and seeing the streetlights twist into elegant crescents. That's what astronomers saw in the distant universe. Faint smears of light, stretched into shimmering arcs that trace the shape of gravity's invisible landscape. Each arc is a whisper from a galaxy too far and faint to see otherwise, its light magnified by the curved glass of space-time. Even more astonishing, the distribution of these distortions across the sky revealed that dark matter isn't spread evenly. It clumps and knots, forming the skeleton of the cosmic web, the framework around which galaxies and clusters gather. Computer simulations confirmed this picture. Invisible filaments of dark matter weaving through the universe, like threads of silk holding the bright beads of galaxies in place. And so, gravitational lensing became both proof and portrait, the universe's way of drawing its own map with the light it bends. It showed us that we live inside a vast network of unseen matter, stretching hundreds of millions of light years, with galaxies glowing along its strands like embers on a web. Einstein once described gravity as geometry with a pulse. When we look at these lenses, we're watching that pulse in action, mass and light performing a slow, elegant dance. Even the equations behind it, filled with curving symbols and Greek letters, can be translated into plain beauty. Where there is mass, light must bow. It's remarkable how the cosmos, in its silence, finds ways to speak. The stars tell one story with brightness, the galaxies another with their motion, and now light itself whispers yet another. That what holds everything together cannot be seen, only traced by its effects. Gravitational lensing doesn't just prove dark matter, it lets us see where it lives. When astronomers colour in their maps based on these measurements, they reveal vast halos around galaxies, hidden valleys of mass between clusters, and even the faint outlines of cosmic rivers where matter flows unseen. Each lens we find adds another line to the universe's invisible sketch. When you look at the images from space telescopes, the glowing arcs, the mirrored galaxies, the delicate circles of light, you are seeing not illusion, but structure. Those are the fingerprints of gravity, the signatures of dark matter bending starlight as it travels across billions of years. And perhaps there's something poetic about it too. For all our instruments and mathematics, the universe still reveals its secrets the way an artist might, through shadow, reflection, and distortion. It doesn't hand us answers. It invites us to interpret the patterns it leaves behind. The more we look, the more we realise that what we call dark is not absence at all. It's presence, hidden just beyond the reach of light. The galaxies continue to spin, light continues to bend, and somewhere in the quiet distances between them, dark matter continues its silent work, shaping, holding, and reminding us that the universe is not built merely from what shines, but from what endures unseen. By the 1980s, astronomers had grown confident that dark matter was real. Rubin's spirals and Einstein's curved starlight had revealed that invisible gravity was sculpting the universe on every scale. But no one yet knew what the universe looked like as a whole. Was it a random sprinkling of galaxies, scattered like dust in a sunbeam? Or did the cosmos have shape and pattern, a larger design woven through its darkness? The question led to one of the most ambitious efforts in astronomy, to create a map of everything. A map not of coastlines or continents, but of galaxies, spread across billions of light years. It would become humanity's attempt to see the structure of the universe from the outside, to trace the invisible threads that connect the stars. At Harvard Center for Astrophysics, two astronomers, John Hochra and Margaret Geller, began the painstaking work of charting galaxies one by one. Each night they collected light through large telescopes, splitting it into rainbows with a prism so they could read each galaxy's speed and distance. The process was slow, like painting a vast mural dot by dot. From these measurements they could calculate something extraordinary, where in the expanding universe each galaxy actually sits. When the data were finally plotted, what emerged was astonishing. The galaxies were not distributed evenly. Instead, they gathered in clusters and sheets, linked by long, thin filaments. Between them lay immense empty spaces, cosmic voids, where almost nothing existed at all. It looked like a sponge, or perhaps a honeycomb, dense walls surrounding vast bubbles of emptiness. The universe was not uniform, but delicately structured, a frozen foam of matter and space. The discovery was both beautiful and humbling. On a map, those glowing dots, the galaxies, were the visible peaks of something much larger and invisible. The filaments that tied them together were made mostly of dark matter, stretching across hundreds of millions of light years. Like veins beneath skin, they gave the cosmos its hidden anatomy. If you could step outside the universe and look back, it might resemble a vast web glistening with dew, each droplet a galaxy cluster, each strand a filament of dark matter. The light from stars traces only the faint outlines of this web, but gravity feels the whole of it. It is through this invisible lattice that galaxies formed, gas flowed, and the first stars ignited. These early maps became the seed for even greater surveys. The Sloan Digital Sky Survey, for instance, would later map more than 1 million galaxies, its computers drawing intricate patterns that stretched across the visible universe. But the concept, the realization that the universe has texture, was born with those early measurements. Astronomers began to speak of the cosmic web. It's a poetic phrase for a scientific truth. That structure itself comes from imbalance. If the universe had been perfectly smooth after the Big Bang, there would be no galaxies, no stars, no us. The faint ripples in matter density, tiny variations from one region to another, gave gravity something to work with. Over billions of years, those ripples grew into filaments and clusters. In the emptier regions, gravity pulled matter away, leaving behind yawning voids, some hundreds of millions of light years across. Imagine bread dough rising in an oven. Pockets of air expand between the denser regions, giving the loaf its texture. The universe, too, expanded unevenly. The dense parts grew into galaxies, while the voids became its airy spaces. Astronomers sometimes call this pattern the large-scale structure, but it might just as well be called the universe's fingerprint. Unique, complex, and softly chaotic. Dark matter, slow-moving and cold, was the invisible yeast that made this structure possible. It gathered first, pulling ordinary matter, the protons, electrons, and atoms, into its gravitational embrace. Without that hidden scaffolding, the visible universe could not have taken shape. Stars would never have coalesced. Galaxies would never have spun themselves into spirals. It's a curious thing. The same substance that hides from light has been, from the very beginning, the organizer of light itself. We owe the arrangement of everything visible to what we cannot see. Supercomputer simulations would later bring this idea to life in astonishing detail. Astronomers fed equations of gravity, expansion, and particle physics into machines powerful enough to follow the universe's growth from its first second to its present age. On their screens, they watched galaxies form like condensation on a window pane, glowing along invisible ridges of dark matter. The resemblance to real observations was uncanny. It was as if the universe itself had been rendered in reverse, beginning from chaos and quietly arranging itself into order. Even the cosmic microwave background, the faint afterglow of the Big Bang, holds the blueprint of this structure. In its subtle temperature variations, only a few millionths of a degree, lie the seeds of every cluster and filament that would later form. Those small wrinkles, magnified over time by gravity, grew into the vast foam we see today. The universe, from its earliest breath, carried the imprint of the invisible hand that would shape it. If you could drift between the galaxies, through the filaments of the cosmic web, the journey would be quiet and nearly empty. You might pass a lonely cluster of galaxies glowing faintly, then enter a region so vast and vacant that no light would reach you for hundreds of millions of years. And yet even there, dark matter would be present, weight without colour, structure without form, gently tugging on everything it touches. This is the strange paradox of existence. We live inside an architecture that is mostly unseen. The Great Wall of galaxies, the voids, the filaments, they all emerge from something that neither emits nor reflects light. We know it only by its gravity, by the way it shapes the motion of stars and the bending of starlight. When you look up at the night sky, you're seeing the bright frosting on an invisible cake, a hint of a vast pattern too large for any telescope to capture in a single view. Every speck of starlight rests on unseen scaffolding. Every cluster of galaxies marks a node in a cosmic network billions of years in the making. And somewhere in that web, on a small branch inside a minor galaxy, we are here, thinking about it. Our atoms, our thoughts, our very existence owe themselves to the gentle pull of something we cannot see or touch. It's comforting in a way. Even in the deepest darkness, structure emerges. Even the unseen has purpose. The cosmos, like a living organism, seems to grow bones before it grows flesh. And in those bones, the pattern of everything else is set. As the great cosmic web took shape, another question began to form beneath it. What exactly was this unseen material that pulled the universe together? Dark matter wasn't just invisible, it was peculiar. It seemed to have mass but no colour, gravity but no light. It neither emitted energy nor absorbed it. It didn't collide, clump, or glow. It was, in a sense, pure structure, an invisible scaffolding on which everything visible was built. But what made it behave that way? What gave the universe its hidden bones? Astronomers began to look backward, to the very first moments after the Big Bang, when the universe was still glowing with the light of its own birth. Back then, everything, matter, radiation, space itself, was mixed together in a hot, dense soup. But even in that fiery chaos, tiny imperfections existed. Some regions had slightly more matter than others, differences as small as 1 part in 100,000. It doesn't sound like much, but these small variations would become the foundation of cosmic architecture. Gravity is patient. It doesn't need drama. It needs time. Over billions of years, those slightly denser regions pulled in surrounding matter. The lighter areas grew emptier, and the denser ones became knots. Hydrogen and helium gas followed, flowing along invisible channels of gravity carved by dark matter. Eventually, those knots became the first stars, the first galaxies, and later, the grand filaments and walls that stretch across space. The nature of dark matter itself was crucial to this story. Whatever these particles were, they had to move slowly. If they had been fast, racing through space at near light speed, they would have smeared out those tiny density differences before galaxies could form. The universe would have stayed smooth, without texture or structure. But something about dark matter allowed it to linger, to clump, to build. Astronomers began calling it cold dark matter. Not because it was cold like winter air, but because it moved sluggishly, as if the cosmic temperature had drained its energy. In the physics of the early universe, cold simply means slow. These particles drifted gently through the expanding fabric of space, letting gravity do its quiet work. They didn't collide or interact like normal atoms. They simply gathered, forming halos, vast invisible spheres of matter that cradled galaxies long before the first stars had even finished burning. If we could see these halos directly, every galaxy would sit like a glowing bead inside a translucent shell, the visible stars no more than a firefly's glimmer within a ghostly sphere hundreds of thousands of light years across. This slow dance of dark matter shaped everything that followed. Without it, the cosmic web would have been fragile, unable to hold itself together. The atoms that make up stars, planets, and people would have drifted too far apart to ever meet. Even the familiar constellations above our heads are only possible because of the steady, patient hand of this unseen matter. Simulations of cosmic evolution show it vividly. When scientists feed the laws of gravity and expansion into a supercomputer, they can watch the universe unfold in miniature. They start with a cloud of tiny dots representing dark matter and let time flow. At first, the dots move almost randomly, like grains of dust floating in still air. But slowly, filaments begin to form. Nodes appear where the threads intersect. Then, as ordinary matter follows those invisible lines, the dark shapes glow with light, the first galaxies igniting in the soft fog of cosmic dawn. It's a sight so mesmerizing that even physicists, usually cautious with words, describe it with wonder. The universe, born from quantum fluctuations too small to imagine, blossomed into galaxies and stars because of dark matter's steadiness. The coldness of those particles was not a defect, it was a design. And yet, what are these particles? No one knows. They may be entirely new forms of matter, tiny, elusive things that pass through you and me every second without leaving a trace. They could be weakly interacting massive particles, as some theories propose, or even more exotic entities with names that sound almost whimsical. Axions, sterile neutrinos, superpartners from a world beyond the standard model of physics. Each of these names represents a hypothesis, a different way the invisible might behave, but they all share one common theme. They're slow, silent, and vast in number. Astronomers can't see them, but they can feel their presence through gravity's imprint. The gravitational field of dark matter is what bends starlight into arcs and lenses, what anchors clusters together, what shapes the rotation of galaxies. Gravity, after all, is the only conversation dark matter seems willing to have. Even the cosmic microwave background, the afterglow of the Big Bang, whispers of dark matter's quiet influence. The tiny variations in temperature across that ancient light tell us how matter behaved when the universe was less than 400,000 years old. The patterns match perfectly with a universe dominated by something non-luminous and slow. a universe with dark matter. If you were to translate those cosmic ripples into sound, they'd form a faint low hum, a kind of primordial music that dark matter composed by tugging gently on everything else. It's strange to think that the same unseen mass that shaped galaxies also left a signature in the oldest light we can observe. It's as if the universe has been humming its own origin story ever since, the melody carried by the invisible. Today, physicists build enormous underground detectors, waiting for dark matter to make itself known. They fill vast tanks with liquid xenon, hoping to catch a rare collision between one of these ghostly particles and an ordinary atom. So far, they've heard nothing but silence. But that silence too is a clue. It tells us that if dark matter exists, and all evidence says it must, it's far more subtle than we imagined. Perhaps that's the point. The things most essential to structure and stability are often the ones we never notice. The scaffolding hidden beneath a cathedral, the bones beneath the skin, the dark matter beneath the stars, they hold everything in place without demanding to be seen. As the universe expanded and cooled, dark matter kept building, patiently collecting the luminous gas that would become stars and worlds. It didn't need light to do its work. It simply waited, and gravity did the rest. Every night sky we look at is its masterpiece, a tapestry woven from both the seen and the unseen. In the stillness between galaxies, in the emptiness of intergalactic space, its presence continues, a silent architect whose greatest design is invisibility itself. The deeper scientists searched for the identity of dark matter, the more they realized they might be chasing a ghost. It pulled with gravity, shaped galaxies, and yet refused to leave any other trace. So they turned to the smallest building blocks of nature, to the world of particles so tiny they drifted through solid rock, through planets, even through people, without ever slowing down. Maybe, they thought, the universe's hidden mass wasn't something exotic at all. Maybe it was made of particles we already knew but had never truly understood. The story began in the early 1930s with a mystery in radioactivity. When physicists studied certain atoms that decayed, spitting out electrons from their nuclei, they noticed that the outgoing particles didn't carry all the energy they should. It was as if something invisible had quietly taken a share before disappearing. That missing energy puzzled one man in particular, the Austrian physicist Wolfgang Pauli. Rather than accept that the law of energy conservation had broken down, he proposed a daring idea. Another particle must be escaping unseen, carrying away the missing energy. He called it, almost apologetically, the neutron. A few years later, when another scientist discovered the actual neutron, a much heavier particle, Pauli's invisible one was renamed the neutrino, meaning little neutral one. It was a ghost among particles, no electric charge, almost no mass, and so shy that it could travel through light years of lead without ever colliding with anything. It would take 2 decades before anyone could detect one. In the 1950s, researchers built huge detectors near nuclear reactors where neutrinos were produced in staggering numbers. Out of billions upon billions, only a few left faint flashes of light in the detectors. They were real, but elusive, slipping through the universe like whispers through fog. When cosmologists began to reckon with the missing mass of the universe, neutrinos seemed like a perfect fit. They were everywhere, produced in enormous quantities during the first seconds after the Big Bang. Even if each one was unimaginably light, their combined mass could be enormous. The early calculations were hopeful. Perhaps the universe's invisible weight came from an ocean of neutrinos, passing through every planet, star and galaxy like a gentle cosmic breeze. But as measurements improved, the picture changed. Experiments showed that neutrinos were far too light and far too fast. They raced through space at nearly the speed of light, refusing to slow down long enough for gravity to gather them into the dense structures we see. If dark matter were made entirely of such restless particles, the universe would have stayed smooth. The delicate filaments of the cosmic web would never have formed. Galaxies would have blurred into the void. So neutrinos were ruled out as the main ingredient of dark matter. They were, in a sense, too quick to settle down, too restless to build. Scientists sometimes call this type of matter hot dark matter, not because it glows, but because its particles move swiftly, like sparks in a storm. What the universe needed was the opposite, something cold and slow. Even so, neutrinos remained fascinating. They were proof that nature could make matter almost invisible, proof that the fabric of reality was more flexible than we imagined. Over the years, researchers discovered that neutrinos could even change identity, shifting between three types as they travelled: electron, muon, and tau neutrinos. It's as though you tossed a blue marble into the air, and by the time it landed, it had quietly turned red or green. This shape-shifting behaviour implied that neutrinos had a mass, albeit vanishingly small. The discovery of that tiny mass earned a Nobel Prize and deepened the mystery. If neutrinos weren't dark matter, what else could exist that was even stranger? Heavier, quieter, and more reluctant to show itself. The question echoed through laboratories and observatories alike. The neutrino story is a reminder of how close science can come to the truth and still miss by a hair. For a while, the world seemed ready to believe that the same particles streaming through our bodies each second might also be the invisible glue of the universe. The idea was elegant, the ordinary and the cosmic joined by a thread of lightness. But the universe had chosen a subtler architect. Still, neutrinos play their own silent role in cosmic history. In the very first moments after the Big Bang, when the universe was less than 1 second old, neutrinos streamed freely through the newborn cosmos, carrying energy away and helping it cool. Even today, billions of them cross every square centimetre of Earth each second, remnants of that first cosmic breath. They are living fossils of the universe's earliest era, older than atoms, older than stars. Physicists continue to chase their secrets. They build enormous underground caverns filled with ultra-clear liquids, waiting for the faint spark that appears when a neutrino finally collides with an atom. The experiments run for years, recording silence upon silence, hoping that one day the quiet will be broken by a flash of truth. Some have even proposed the existence of a fourth type of neutrino, a heavier, sterile cousin that interacts only through gravity. If such particles exist, they might bridge the gap between known physics and the dark sector. The name itself, sterile, carries a strange poetry, something real, yet untouchable, influencing the cosmos from the shadows. But so far, evidence for this hidden cousin remains elusive. The search continues because neutrinos hint at a lesson larger than themselves. They remind us that invisibility doesn't mean absence. The universe is full of things we cannot feel directly, yet that shape us in ways we barely notice. Like the wind that sculpts dunes or the ocean current that steers entire ecosystems, these faint particles leave their mark by persistence, not by display. When you pause and think about it, the story of neutrinos is really the story of humility. It teaches us that what feels solid and knowable is only a small part of reality. We are surrounded by a sea of motion too fine for our senses, a quiet river of particles passing through the world, through us, without ever disturbing the air. Dark matter would have to be something else, slower, heavier, more obedient to gravity's call. But in searching for it, scientists found something almost as valuable, a glimpse of how subtle the universe can be. The neutrino may not explain the missing mass, but it reminds us that even the smallest mysteries can open doors to the grandest truths. In the end, the neutrino wasn't enough, but it was a start. It showed us that the universe doesn't hide out of cruelty, it hides out of complexity. And sometimes the first step toward finding what's truly dark is learning to listen to the faintest light that passes through. After the neutrino's graceful exit from the list of suspects, scientists turn their eyes back to the sky. If dark matter wasn't made of fast, tiny particles, perhaps it was something far larger, something massive enough to sculpt gravity itself. And what better candidate than the most mysterious objects known to physics, black holes? The idea was as old as Einstein's equations and as haunting as the night sky itself. Black holes are regions where gravity becomes absolute, where light itself curves inward and never returns. If enough of them drifted unseen between the stars, their combined weight could account for the universe's missing mass. They would be the perfect culprits, dark by nature, invisible by design. There was even a poetic symmetry to it. The first clue to dark matter had come from galaxies moving too fast. What if, hidden among those galaxies, countless black holes were anchoring them with unseen gravity? The notion had elegance, and for a time excitement spread through the astrophysical community. But there was a problem of scale. Black holes come in different kinds. The ones born from dying stars, stellar black holes, are relatively small, perhaps a few times the mass of our Sun. The ones that anchor galaxies, the supermassive variety, are millions or billions of times heavier. Neither seemed abundant enough to fill the universe's gravitational gap. So theorists proposed a new kind, something left over from the earliest moments after the Big Bang, primordial black holes. These wouldn't form from collapsing stars but from dense knots of energy in the newborn universe itself. If the early cosmos had contained regions just a little too heavy, gravity might have crushed them into black holes almost instantly. Some could be as small as mountains, others as heavy as Earth, drifting silently through the cosmos. If they existed in enormous numbers, they could make up all the dark matter, tiny seeds of gravity scattered through space. It was an alluring thought, the darkness explained by darkness itself. But how could anyone test it? After all, black holes don't emit light. They reveal themselves only by what they influence, the stars they tug, the light they bend. So astronomers designed a way to look for them indirectly, using a delicate trick of nature called gravitational microlensing. Imagine watching a distant star twinkle far across the galaxy. If a compact object, a black hole, or even a planet, passes directly in front of it, its gravity briefly focuses the star's light, making it appear a little brighter. The effect lasts only days or weeks, a tiny flare of borrowed light. Detecting such events is like waiting for a single leaf to drift across the face of a distant street lamp. But if black holes were truly numerous, these flares should happen regularly. Throughout the 1990s, teams of astronomers aimed their telescopes at dense fields of stars, particularly toward the Large Magellanic Cloud, a small neighbouring galaxy rich with targets. For years they watched, recorded, and waited. Every brightening, every flicker was logged and measured. The data trickled in. A few events appeared promising, gentle upticks in brightness that lasted about a month, just as predicted. But the numbers were too few. After a decade of patient watching, it became clear that black holes could not make up the bulk of dark matter. There simply weren't enough flares. The universe's hidden weight had to come from something else. Still, the effort was not wasted. These microlensing experiments, though born of disappointment, taught astronomers to measure gravity's fingerprints with exquisite precision. They began to use the same method to detect planets around distant stars, and even to probe the shape of the Milky Way's halo. Each failure deepened understanding, and each silence revealed what the dark matter could not be. In hindsight, the search for primordial black holes feels like a quiet lesson in humility. The universe had offered an elegant possibility, and we had followed it with faith and persistence, only to find that the truth was more elusive. The dark matter wasn't a collection of invisible monsters scattered through space. It was something gentler, subtler, something that refused to reveal itself even under the watchful gaze of telescopes. And yet, the idea of primordial black holes never fully died. It lingers at the edges of science, revived now and then when new evidence surfaces. Some physicists suggest that they could still exist in small numbers. They're rare mergers producing gravitational waves, ripples in space-time that instruments like LIGO can detect. The discovery of those waves in 2015 reignited a quiet spark of hope. Could some of the colliding black holes detected by LIGO be ancient ones, born in the first second of the universe? If so, perhaps a fraction of dark matter hides in those invisible relics. For now, though, they remain curiosities, too few to solve the puzzle, too strange to dismiss. The failure of the black hole hypothesis left cosmologists with mixed feelings. On one hand, it ruled out yet another possibility. On the other, it reminded them that the search itself was meaningful. Every path, even the wrong ones, narrows the space in which the truth can hide. Like explorers mapping an uncharted island, scientists mark the places where the treasure isn't, slowly closing in on where it might be. The image of a black hole remains one of the most powerful symbols in astronomy, the universe's ultimate secret, a hole in space-time itself. Yet when it comes to the mystery of dark matter, the real answer seems to lie not in holes, but in wholeness, in the quiet gravitational fabric that fills everything between. To picture the truth, imagine the galaxy as a city at night. The stars are its streetlights, the glowing outlines of familiar landmarks. But the roads, the bridges, and the empty spaces between, the infrastructure that holds it all together, are invisible in the dark. Dark matter is that unseen architecture, more pervasive than the lights themselves. The black holes might be dramatic, but they are exceptions, not the rule. As the 20th century came to an end, the list of suspects had been narrowed but not resolved. Neutrinos were too light. Black holes were too rare. Some new form of matter must exist, silent, yet abundant, shaping the cosmos in ways we were only beginning to grasp. The universe, patient as ever, kept its secret. And the scientists, patient too, kept watching. In every unlit corner of the sky, they saw the same message written in gravity's language. There is more here than meets the eye. Perhaps that's the truest lesson of all, that even disappointment can be a kind of discovery. It reminds us that the universe doesn't owe us answers. It offers us paths. And sometimes, the long way around is the only road that leads to wonder. By the turn of the century, the list of suspects behind dark matter was shrinking. Neutrinos were too light and too restless. Black holes were too rare. And yet the invisible mass still made up nearly a quarter of the universe, quietly shaping galaxies and binding the cosmic web. Astronomers could trace its pull across space, but physicists wanted to know what it actually was. Somewhere, they believed, there had to be a particle, something silent, stable, and heavy enough to give gravity its unseen grip. It was then that attention turned inward, into the world of subatomic puzzles. In the heart of particle physics, there lived a strange imperfection. The equations describing the strong force, the powerful glue that holds atomic nuclei together, allowed for a kind of imbalance, a broken symmetry that should have produced measurable effects. But nature seemed too neat for that. Experiments showed the symmetry was intact, perfectly behaved, almost unnaturally tidy. To fix this inconsistency, two theorists, Roberta Peccei and Helen Quinn, proposed a clever mathematical repair in the late 1970s. Their solution came with an unexpected bonus. It predicted a new particle, something very light, very calm, and almost impossible to detect. A particle that would clean up the mess in the strong force equations and restore harmony to physics. When Nobel laureate Frank Wilczek read about it, he decided this neat little particle deserved a neat little name. He borrowed it from a brand of laundry detergent, Axion, because as he joked, it cleaned up a problem in physics. It was an unassuming beginning for one of the most intriguing ideas in cosmology. What had started as a technical correction in a theoretical model soon became a leading candidate for dark matter. The axion, by its very nature, would be invisible, almost non-interacting, but present everywhere. In the vastness of space, countless axions could drift like a cosmic fog, their combined mass enough to hold galaxies together. The beauty of the axion theory lay in its simplicity. If the universe needed dark matter and physics needed balance, perhaps the same gentle particle could satisfy both. It was a poetic solution, a bit of housekeeping on the smallest scale solving one of the largest mysteries of all. Physicists began searching for axions in creative ways. They built exquisitely sensitive detectors to listen for faint signals. Some experiments tried to turn magnetic fields into radio receivers, hoping to catch the faint whisper of an axion turning into a photon. Others looked for tiny distortions in cosmic radiation, small ripples that these particles might have left behind in the early universe. The silence, however, persisted. But science often moves forward not with discoveries, but with non-discoveries. Every failure teaches where not to look, how not to expect, and what new doors might be opening. And as the search for axions deepened, another idea emerged: supersymmetry. To most of us, symmetry is simple. Two wings of a butterfly, the balance of a leaf, the way reflection mirrors shape. But in the equations that describe particles, symmetry can mean entire families of hidden relationships. Supersymmetry suggests that every known particle has a heavier, unseen twin. Electrons would have selectrons, quarks would have squarks, and photons would have photinos, shadows of the light itself. The names, given half in jest, sound whimsical, but behind them lies a profound idea. The universe might contain a second mirrored layer of matter, softly folded beneath the one we see. If this shadow world exists, one of its members could be the long-sought dark matter particle. It would be massive enough to account for the missing gravity, stable enough to persist for billions of years, and invisible to everything except gravity itself. Scientists nickname these hypothetical particles WIMPs, short for weakly interacting massive particles. The name sounds playful, but the concept is serious. If they exist, trillions pass through us every second, silent and harmless, like a breeze made of ghosts. Supersymmetry, the axion, the WIMP, each offers a vision of the invisible, a way for the unseen to exist without contradicting the seen. None has yet been proven, but together they paint a portrait of a universe more intricate than any we could have imagined. When you listen to physicists describe these possibilities, their tone is often surprisingly tender. They talk about elegance, beauty, balance, as if they were describing art rather than algebra. The equations, full of Greek letters and abstract symbols, are really just a language for describing harmony and imperfection. And in that harmony, they hope to find the shadow that explains why galaxies stay whole, why clusters bind, why the cosmic web holds its shape. In one sense, the axion is less a particle and more a promise that the universe's messiness might still make sense. Frank Wilczek once wrote that the axion, if found, would make physics beautiful again. There's something quietly human about that desire, to believe that even in chaos, symmetry will eventually return. Today, vast experiments continue the search. Deep underground, tanks of liquid xenon wait for the faintest nudge of an unknown particle. In remote observatories, instruments tuned to radio frequencies listen for the faint hum that axions might produce in magnetic fields. Space telescopes scan for clues in the glow of the early universe. So far, there's been only silence, but it's a meaningful kind of silence, the kind that invites patience. In truth, if axions or supersymmetric particles are out there, they may never be caught in the traditional sense. They might reveal themselves only through their collective behaviour, through the graceful curves of galaxies and the persistence of cosmic structure. They may remain, as dark matter itself has always been, a story told in gravity's handwriting rather than in light's, and perhaps that's fitting. The axion began as a particle meant to restore order, a cosmic detergent for messy equations, and became a symbol of how the universe often hides its solutions in elegance rather than simplicity. Even in the deepest mystery, there is a kind of tidiness, a sense that nature prefers beauty over chaos. If you imagine the cosmos as an unfinished painting, the axion might be the invisible brushstroke, the faint correction beneath the colour, the detail you don't notice but that makes the whole image feel right. Whether or not it's ever found, it has already changed how we think about the unseen. In the end, the axion teaches a subtle truth. Not every discovery needs to be visible. Some ideas, like some forms of matter, do their work quietly, holding the universe together not by shining, but by keeping it balanced. And in that balance, perhaps, lies the real beauty of the dark. By the early years of the 21st century, the search for dark matter had moved beyond theory. Physicists had filled deep caverns with detectors and surrounded them with mountains of rock to block unwanted noise. They had tuned antennas to frequencies so faint they bordered on silence, hoping to hear the soft hum of invisible particles. Yet the universe, patient as ever, kept its secret. And so, as scientists so often do, they looked up again. Perhaps the clue wasn't in what dark matter left behind on Earth, but in what it might leave behind in the sky. They began to search for light born from darkness, radiation that could reveal where unseen matter hides. The idea was simple, but elegant. If dark, matter particles could collide with one another, they might annihilate in tiny flashes of energy, creating ordinary light in the form of high-energy gamma rays. These photons, so energetic they can pass through steel or stone, could travel across the galaxy and tell us where the invisible gathers. Astronomers turn their most sensitive eyes toward the centre of the Milky Way, the crowded heart of our spiral galaxy, where billions of stars orbit a supermassive black hole. If dark matter forms a halo around every galaxy, then the centre, where gravity is strongest, should be where it is densest. And if these hidden particles truly destroy each other when they meet, the galactic heart should glow with a faint, mysterious light. In 2008, NASA launched the Fermi Gamma Ray Space Telescope, a satellite built to listen to the universe's highest energy conversations. Over the next few years, it gathered photons from across the sky, mapping bursts from exploding stars, jets from black holes, and even faint glimmers from the edge of known space. Then, as researchers sifted through the data, they noticed something odd, a persistent glow near the centre of the Milky Way that couldn't easily be explained. It wasn't a single point, like a star or a black hole, but a soft haze stretching across the galactic core. Some called it the galactic centre excess, a phrase that sounds clinical but hides kind of quiet astonishment. The glow was made of gamma rays with energies that seemed to fit the predictions for dark matter annihilation. It was as if the invisible mass of the universe had momentarily betrayed its presence, whispering in flashes of light. The numbers, when written down, had the rhythm of a heartbeat. But science is cautious, and caution often turns wonder into discipline. Other astronomers pointed out that the centre of our galaxy is a busy place, filled with pulsars, magnetic fields, clouds of gas, and tangled filaments of energy. Perhaps the glow came not from exotic particles, but from an army of tiny spinning stars, each one too faint to see individually. The argument became a kind of cosmic tug-of-war. Was this the signature of dark matter, or just the galaxy breathing? As the debate unfolded, the glow itself remained silent. It neither brightened nor faded. It simply existed, a faint shimmer in the data, as if waiting for us to decide what it meant. Even today, after more than a decade of study, the question remains unresolved. The galactic heart still shines with its quiet excess, a reminder that sometimes even the smallest mysteries can stretch across thousands of light years. There's a poetic irony to it. For decades, dark matter had revealed itself only through gravity, through the way it shaped motion and bent light. Now it might also be speaking through light itself, a whisper from particles destroying one another in the depths of space. The very act of disappearance could be what makes them visible. When you look at images from the Fermi telescope, you don't see bright dots or colourful spirals. You see patterns of energy, delicate gradients like faint brushstrokes across a dark canvas. The galactic centre looks almost like a lantern glowing behind mist. The light is there, but it diffuses gently, never shouting its presence. It's easy to imagine that if the universe could exhale, this is what it would look like, a slow golden breath in the dark. These subtle patterns have inspired many new searches. Some scientists have begun scanning dwarf galaxies, tiny companions of the Milky Way that contain very little ordinary matter but are rich in dark matter. If the same glow appears there, it would be difficult to dismiss it as ordinary astrophysics. Others look toward clusters of galaxies, or even to the cosmic background itself, where faint ripples of high-energy light might tell of ancient annihilations that took place billions of years ago. So far the results are mixed. Some observations strengthen the case for dark matter's hidden glow, others dim it. But uncertainty is not failure. It's the space where imagination and evidence meet, where the universe invites us to keep asking questions. Every photon that arrives carries a sliver of information about what lies unseen. And so, the story of the galactic centre excess continues, half science, half poetry. If you were to translate it into sound, it might resemble a faint hum, rising and falling with the rhythm of orbits and collisions. Some physicists even compare it to cosmic music, a background melody composed by particles we can't yet name. For the dreamers among them, this glow is a sign of hope. It says that the invisible doesn't stay silent forever. It finds ways to speak in the only language the universe knows, light. For the skeptics, it's a warning to listen carefully, to separate whispers from echoes. Both perspectives are necessary. The cosmos, after all, thrives on balance, discovery and doubt, wonder and patience. Perhaps the most beautiful outcome of all this searching is what it teaches about perspective. We live inside a galaxy that is itself alive with mysteries. When you stand under the night sky and see the faint arch of the Milky Way, you're looking at billions of suns bound together by an invisible halo, glowing at its core with light we can barely measure. We are not outside observers, we're inside the glow, part of the same quiet pattern we're trying to understand. In the coming years, new instruments, more sensitive and more patient, will continue to study that galactic heart. They'll look for subtle changes in the brightness, for spectral fingerprints that might distinguish dark matter from pulsars, for symmetry in the glow that might hint at a deeper design. Whether or not they find a clear answer, the search itself will remain one of the most delicate acts of listening ever attempted by humankind. The universe never rushes to reveal its truths. It prefers slow revelations, hints left like footprints in starlight. And in that soft golden haze at the centre of our galaxy, there may yet lie the first true glimpse of the invisible, the quiet shimmer of darkness turning, for a moment, into light. By the late 1990s, cosmology had reached an almost comfortable place. The age and size of the universe were roughly known. Its shape was mapped in exquisite detail through galaxy surveys. Dark matter had taken its seat in the cosmic budget, invisible yet accepted. Most astronomers believed the universe's expansion, born from the Big Bang, was gradually slowing under gravity's pull. Like a ball thrown upward, it would rise for a time, slow down, and perhaps one day fall back. The question seemed simple. How fast was the universe slowing down? Two teams decided to find out. One was called the Supernova Cosmology Project, led by Saul Perlmutter in California. The other, the High Z Supernova Search Team, was led by Brian Schmidt in Australia, with Adam Rees among its youngest members. Their goal was to measure how the rate of cosmic expansion had changed over billions of years. The tools they chose were distant explosions, type Ia supernovae, the spectacular deaths of white dwarf stars. These cosmic detonations are among the most reliable lights in the universe. Each one releases about the same amount of energy, shining with a predictable brightness that can outshine an entire galaxy for a few weeks. Because their true luminosity is known, astronomers can use them as standard candles. Measure how bright one appears, and you can calculate its distance. Compare that distance with how much its light has been stretched by the expansion of space, the redshift, and you get a snapshot of the universe's history. The two teams scoured the sky, using some of the world's largest telescopes on mountaintops and in orbit. They combed through thousands of images looking for new points of light that hadn't been there the week before. Every discovery was a fleeting signal, an old star dying in a faraway galaxy, its final blaze travelling across billions of years to reach Earth. Each supernova, like a cosmic mile marker, recorded the pace of expansion at the moment it exploded. The expectation was clear. The combined gravity of all the matter and radiation in the universe should slow expansion over time. Galaxies should drift apart more and more slowly as the cosmic clock ticked forward. The teams worked separately, carefully, quietly, comparing their data, calibrating instruments, and refining their calculations. Then came the shock. The supernovae were too faint. They were dimmer than they should have been if the universe was slowing down. The only explanation was that these galaxies were farther away than expected, which meant that the expansion of the universe had been speeding up, not slowing down. It was a result so strange that both groups doubted their own data. They checked for dust that might be obscuring the light, for calibration errors, for selection bias, anything that could explain away the conclusion. But the evidence held. The cosmos was not being reined in by gravity. It was accelerating, stretching faster and faster, as though something unseen were pushing it outward. In early 1998, both teams published their findings. The reaction was a mixture of disbelief and awe. The universe, it seemed, had a secret engine. Something invisible was working against gravity, driving galaxies apart. It was as if, after billions of years of slowing, the universe had suddenly decided to run. They called this mysterious phenomenon dark energy. It wasn't a name that explained much, but it captured the essence, an unseen force, filling all of space, with a gentle yet relentless pressure that made the cosmos expand faster. It wasn't energy in the ordinary sense. No light, no heat, no radiation. It was more like a property of the universe itself, a quiet tension woven into the fabric of space. When the dust settled, the numbers told a new story of cosmic composition. Only about 5% of the universe was made of ordinary matter, the atoms that formed stars, planets, and people. About 25% was dark matter, the invisible glue that holds galaxies together, and the remaining 70%? Dark energy, the invisible push that tears them apart. The universe, it turned out, was dominated by something we had never seen and could barely describe. Imagine that for a moment. All the light we can see, all the galaxies that fill our telescopes, all the stories written in starlight. Together they form only a tiny fraction of what exists. The rest is a quiet duality. Dark matter pulling inward, dark energy pushing outward. A cosmic tug-of-war played on scales so vast they defy imagination. In 2011, Saul Perlmutter, Brian Schmidt and Adam Rees received the Nobel Prize in Physics for the discovery. but the true reward was the wonder their work inspired. The universe had surprised us again, overturning our expectations with the same quiet mischief it had shown to Zwicky, Rubin and Einstein. What exactly is dark energy? No one can yet say. It might be a property of empty space itself, a faint constant pressure that grows more dominant as the universe expands. Or it could be something dynamic, a field that changes slowly with time, an echo of the same mysterious force that drove the early inflation of the cosmos. Some even suggest that our understanding of gravity might need revision, that perhaps space and time behave differently on the larger scales. But whatever the explanation, one thing is clear. The universe is not coasting towards stillness. It's racing towards something unknown, its pace quickening as galaxies drift apart like embers from a dying fire. If you could watch the night sky over unimaginable spans of time, you would see the distant galaxies fade one by one, redshifted into invisibility by the accelerating expansion. Billions of years from now, the cosmic landscape will look empty, the nearest galaxies too far for their light ever to reach us. The universe, born in a flash of light, will grow darker with every passing eon. And yet, there's something deeply serene about that vision. Expansion is not destruction, it's continuation. The same force that scattered matter across the void also gave rise to structure, stars, and consciousness itself. This same mystery that now drives galaxies apart once made it possible for us to be here, thinking about it. Astronomy has always been the art of reading what light remembers. In the faint glow of ancient supernovae, we found a message billions of years old. The universe is more restless, more alive than we ever dreamed. Its expansion isn't slowing, it's singing. A song too vast for our brief lives to hear in full, but one we can still hum along to in wonder. When the discovery of dark energy was first announced, it felt as though the universe had just whispered a secret from the past, one that had been hiding in plain sight since the early 20th century. The astronomers who found that the cosmos was speeding up rather than slowing down were stunned, but somewhere, quietly smiling through history, was a man who had already written down the answer and then thrown it away. Albert Einstein. Nearly a century earlier, Einstein had been wrestling with his own equations of general relativity, the mathematical framework that described how matter and energy bend the fabric of space and time. Those equations were elegant, so elegant in fact, that they told him something uncomfortable. The natural consequence of his theory wasn't a static, eternal universe, as most people believed at the time, but one that expanded or contracted. To Einstein, that felt wrong. The night sky seemed timeless, unchanging. Galaxies weren't even known to exist yet. The Milky Way appeared to be the whole cosmos. And so, to steady the universe, to keep it from collapsing under its own gravity, he added a term, a gentle counterforce woven into the mathematics. He called it the cosmological constant. This constant, represented by the Greek letter lambda, was like a small, steady pressure that pushed outward on space itself. It acted as an invisible hand balancing gravity's pull, keeping the universe still. It had no name, no origin, and no physical explanation, just a purpose, stability. Einstein thought of it as a kind of mathematical patch, a tiny edit in an otherwise perfect script. Then, in the 1920s, came the observations of Edwin Hubble. Through his telescope at Mount Wilson Observatory, he saw that the light from distant galaxies was stretched, reddened, a clear sign that they were moving away from us. The farther away a galaxy was, the faster it seemed to recede. The universe was expanding. The cosmos didn't need a balancing term. It needed freedom. Einstein, upon hearing this, reportedly sighed and called his cosmological constant my greatest blunder. For decades, physicists took him at his word. The constant was dropped from textbooks, left behind as a curious historical footnote. The universe, we thought, was expanding because of the energy from the Big Bang. its momentum slowly being slowed by gravity. No extra push was necessary. Space itself could breathe naturally. But time has a strange way of circling back. When 70 years later, astronomers discovered that cosmic expansion was not slowing but accelerating, they reached for a familiar tool. To explain this new outward pressure, they brought Einstein's discarded constant back to life. And suddenly, his so-called blunder looked like prophecy. In modern cosmology, the cosmological constant represents what we now call dark energy, the persistent uniform pressure filling all of space, driving galaxies apart faster and faster. It's as if the very emptiness of the universe has a faint tension built into it, a quiet pulse that grows more dominant as everything stretches outward. Einstein's balancing term was no longer a mistake, it was the universe's heartbeat. What does this constant really mean? In simple terms, it suggests that empty space isn't truly empty. Even when you remove every atom, every photon, every particle, there remains something, an energy of the vacuum itself. Quantum physics tells us that the vacuum isn't a void but a restless sea. Tiny virtual particles flicker in and out of existence everywhere, constantly appearing and vanishing like ripples on an invisible ocean. Their collective energy, though nearly impossible to measure directly, might be what drives the expansion of the universe. In Einstein's time, this idea would have sounded absurd. Space was a stage, not a participant. But relativity changed that forever. Space isn't the arena in which the universe happens. It is the universe. It bends, stretches, vibrates, and, as we now know, pushes. The beauty of this revelation lies in its symmetry. At the beginning of our story, Einstein tried to make the universe stay still by introducing a subtle outward force. Later, when the universe was found to be expanding, he removed that force in embarrassment. Now, a century later, the same term, revived, reinterpreted and renamed, has returned as the key to cosmic acceleration. It's as though the universe smiled at Einstein's humility and gently handed his idea back, whispering, "You were right, but not for the reason you thought." There's a poetic charm in imagining Einstein at his desk, frowning over his equations, unaware that he had already written one of the most important clues in cosmology's future. He couldn't have known that the same symbol he scribbled to preserve stillness would one day explain motion itself. The cosmos, it seems, is fond of irony. For scientists today, the cosmological constant remains both a triumph and a torment. It fits the data perfectly, better in fact than almost any other theory. Plug it into Einstein's equations, and the universe's expansion behaves just as the supernova observations describe. Yet it also raises deep, unsettling questions. Why does the constant have the value it does? Why isn't it larger or smaller? If it were even slightly different, galaxies might never have formed, stars might never have lit, and we would not be here to ponder it. The precision feels almost deliberate, and that strangeness sits at the heart of modern physics. We call it a constant, but we don't know if it's truly constant. It might evolve slowly over time, fading or strengthening as the universe grows. Some theories suggest it's connected to an ancient field, the same one that powered inflation, the furious expansion that followed the Big Bang. Others hint that it's a shadow cast by dimensions beyond our comprehension. Yet for all its mystery, the cosmological constant remains our best description of dark energy, the quiet pressure that makes space expand. There's something deeply comforting about that. It suggests that even our mistakes can be seeds of discovery. Einstein, in his desire for stillness, planted the very idea that would later explain motion. What he saw as a blunder became the key to understanding why the universe doesn't just drift, it accelerates. If you look up tonight and imagine the galaxies slowly gliding apart, you can think of lambda, the cosmological constant, as the soft breath between them, a force too gentle to feel, too vast to see, but always present. Not a shove, not a roar, but a whisper. Expansion, expansion, expansion. Perhaps in the quiet of his study, Einstein felt that whisper too. Perhaps deep down, he knew that even the stillness he longed for was only another kind of motion, the steady unfolding of space itself. In the end, what he called a mistake became the universe's most elegant line of poetry, that emptiness is never truly empty, and that the greatest blunders can sometimes turn out to be truths waiting for the right century to understand them. There is a strange kind of silence in the idea of dark energy, an invisible pressure that fills the universe, pushing galaxies apart, yet making no sound. It's not a force in the traditional sense, not a wind or a current or a field that we can feel. It's more like a property of space itself, a subtle tension woven into the fabric of reality. The name dark energy makes it sound dramatic, but its nature is quiet, diffuse, and infinitely patient. To understand it, we have to start with something that sounds almost contradictory. The emptier space is, the more it does. We think of a vacuum as nothingness, but physics tells a different story. Even in perfect emptiness, space is restless. It hums with potential. Tiny fluctuations shimmer in and out of existence. Brief ghost-like particles that appear, interact, and vanish again before we can notice. This ceaseless flicker is a direct consequence of quantum mechanics, a reminder that uncertainty is built into the universe's foundation. In quantum theory, there's a principle that says you can never know both the energy and the duration of an event perfectly. The universe, as if mischievous, takes advantage of this rule. For incredibly short moments, it borrows energy from nothing, creates pairs of particles and their opposites, lets them dance, and then reclaims the energy when they annihilate each other. These pairs are called virtual particles, though that word hardly does justice to their strange existence. They are like the thoughts of the universe, fleeting, real enough to leave traces, but never lingering long enough to be caught. If you could somehow listen to this quantum vacuum, you'd hear not silence, but a soft hiss of creation and destruction happening everywhere, all the time. It's as if emptiness itself is breathing. Physicists once wondered, if all these tiny fluctuations have energy, could their combined effect explain the mysterious dark energy that drives the universe's expansion? It seemed logical. But when they tried to calculate how much energy this restless vacuum should contain, they ran into a problem, one so immense it's often called the worst prediction in physics. According to the equations of quantum field theory, the vacuum energy should be enormous, about 10 raised to the power of 120 times greater than what we actually observe. That's a 1 followed by 120 zeros, a number so absurdly large that it makes the entire cosmos look microscopic by comparison. If the calculation were right, space would be exploding in an instant, tearing galaxies apart faster than light could travel. Clearly that wasn't happening. The universe was expanding, yes, but slowly, gracefully, not violently. Something about our understanding was profoundly wrong. It's difficult even to grasp how big that discrepancy is. Imagine measuring the thickness of a sheet of paper, and your theory predicts the distance from Earth to the nearest galaxy. That's how far off we were. Physicists laughed, grimaced, and then sighed. The vacuum, it seemed, was both everything and nothing, filled with energy that somehow cancels itself out almost perfectly, leaving behind only a faint residue. That residue, many believe, is the dark energy we now see in the cosmos. The idea is both humbling and beautiful, that all of space, even the parts we think of as empty, carries a kind of internal tension, a soft pressure that pushes the universe outward. Unlike the air that presses on your skin, this pressure doesn't come from collisions or particles. It comes from the geometry of space itself, a slow outward sigh written into the structure of reality. To describe this gently, imagine stretching a rubber sheet. The more you pull it, the more it resists, pushing back with equal determination. Dark energy behaves a little like that, except that in this case, the sheet is the universe, and the resistance is reversed. It encourages expansion rather than resisting it. The more the universe grows, the more room there is for dark energy, and the faster it expands. It's a self-feeding quietness, an invisible elasticity of space. Scientists call this phenomenon negative pressure. It sounds odd. How can something negative push outward? But the term simply means that dark energy behaves in the opposite way to ordinary matter. Matter and radiation attract. They pull together. Dark energy repels. It stretches the fabric rather than gathering it. It's the universe's gentle counterpoint to gravity, the yin to its yang. And yet, for all its gentleness, it dominates everything. About 70% of the cosmos is this silent, pushing energy. The galaxies we see, clusters of stars swirling in slow spirals, are the exceptions. The tiny luminous knots floating in a sea of invisible expansion. There's something profoundly meditative about that. We live in a universe defined not by what's there, but by what moves between. The galaxies are like ripples on the surface of an infinite ocean, but it's the ocean's calm depth that dictates the rhythm of the waves. Scientists have tried to go further, to connect the quantum and the cosmic, to find a theory that explains how the jittering of microscopic particles could shape the behaviour of entire galaxies. Some imagine that the vacuum is like a kind of cosmic foam. Tiny, ever-changing bubbles forming and collapsing, giving space its texture. Others picture it as an ocean of fields, humming with potential energy, whose surface tension gives rise to dark energy. But each attempt ends in partial understanding, like trying to describe music when you've only ever seen the sheet notes. The truth might be that the universe is both more intricate and more simple than our mathematics can express. Perhaps dark energy isn't something added to space, but a property of space itself, the natural consequence of existence continuing. Space wants to expand. It doesn't need a reason any more than a flame needs to explain why it flickers. When you look at the stars tonight, their light reaching you from millions or billions of years ago, remember that the very space that carries that light is stretching even now. The distance between every pair of galaxies grows, quietly, in the dark. That expansion is powered not by a storm or explosion, but by the softest force imaginable, the tension in empty space. If there is a lesson hidden in this cosmic mystery, it might be this: even nothing is never nothing. Emptiness has weight, silence has motion, and the void hums with quiet intent. The more we study it, the more it seems that the universe does not fear emptiness, it depends on it. Without that silent pressure, there would be no balance, no structure, no story at all. And so, as the cosmos expands into an ever-deepening night, perhaps it's not running away from something, but growing into itself, guided by the same delicate tension that keeps the stars apart, yet connected by gravity's invisible thread. The vacuum, restless and alive, continues to breathe, and in that breath lies the most astonishing paradox of all, that nothingness may be the source of everything. After so many decades of discovery, astronomy had managed to weigh the universe, yet somehow it still didn't know what most of it was made of. Only about 5% of the cosmos, the stars, the gas, the dust, and all the things that sparkle, consists of familiar matter. The rest remains unseen, roughly a quarter as dark matter, pulling the galaxies together, and nearly 3/4 as dark energy, pushing them apart. Two invisible hands sculpting opposite directions of destiny. For a long time, scientists treated these mysteries as separate puzzles, two problems with two very different personalities. Dark matter, heavy and quiet, gathers things. Dark energy, light and restless, scatters them. One acts like gravity's ally, the other its rival. But in recent years, some have begun to wonder, What if they are not strangers at all? What if these two unseen forces are simply two sides of the same hidden world? A conversation whispered between the shadows. They call it the dark sector, a phrase that sounds almost like poetry. It describes the possibility that dark matter and dark energy might share an origin, a relationship, or even an ongoing dialogue that we've only begun to overhear. Just as the ordinary matter we know comes in many forms, atoms, light, magnetic fields, and forces, the dark sector might have its own richness, its own laws and interactions, quietly mirroring the one we can see. To imagine this, picture the universe as an orchestra. We've been listening to one section, the violins of visible matter, the brass of starlight, the percussion of galaxies colliding. But faintly in the distance there's another ensemble playing. Its instruments are silent to our ears, yet their rhythm shapes the harmony we hear. The music wouldn't sound the same without them. The universe too might be performing a duet of light and dark, each influencing the other through gravity's unseen baton. Some scientists have tried to formalize this intuition. In their equations, dark matter and dark energy are not independent players, but partners exchanging energy and influence. The idea is subtle. If dark matter decays slowly over time, its lost energy could feed the growth of dark energy, explaining why the acceleration of the universe began only recently in cosmic history. In this picture, the dark universe has its own life cycle, matter giving way to expansion, gravity passing the baton to a softer, more diffuse form of energy. Researchers have proposed even bolder ideas. Perhaps dark matter isn't just one kind of particle, but an entire family, particles that interact through forces we don't yet know, forces that have their own dark light and dark radiation. If that's true, our universe might be only half the story, the bright half of a much larger whole. We live in a shared cosmos, where two forms of matter, one visible, one hidden, coexist like overlapping shadows. It's a humbling thought. For all our technological prowess, we still see only a sliver of what's real. The photons that reach our eyes, the atoms that build our world, they're just the visible embroidery on a much grander cosmic fabric. Beneath that layer lies something that doesn't glow, doesn't scatter, doesn't shout, but it moves, it evolves, it responds, it may even listen. When physicists speak about the conversation between dark matter and dark energy, they do so carefully. It's not conversation in the human sense, but the poetry is fitting. Both are parts of the same grand equation, two invisible voices shaping the same silent symphony. One voice deepens gravity's chords, drawing galaxies into clusters. The other raises a high, ethereal note that stretches space itself. The beauty of the cosmos may lie not in which voice dominates, but in the delicate harmony between them. To illustrate this harmony, some cosmologists use a gentle analogy. Imagine a balloon being inflated. The rubber's elasticity corresponds to dark energy, pushing outward, while the specks of dust on the surface represent galaxies held in place by dark matter. The universe grows larger, but the pattern of dust remains, guided by an invisible tension between pull and push. Each moment of cosmic time is a balance between these two unseen players, and yet this balance might not be permanent. If dark matter slowly fades, dark energy may grow stronger, accelerating expansion even further. Conversely, if dark energy changes or weakens, gravity might one day reclaim its throne, and the universe could begin to contract again. These possibilities hint that the cosmos isn't static. It's dynamic, adaptive, perhaps even self-correcting, as if learning to maintain its own equilibrium across eons. There's something deeply comforting in that idea. The universe is not a chaotic explosion. It's a system of relationships. What we call darkness might simply be the other side of connection, the part that acts quietly so that light can shine without collapsing into itself. The cosmos doesn't just exist, it negotiates. In laboratories and observatories, researchers continue to listen for this hidden dialogue. They look for tiny irregularities in the cosmic microwave background, the afterglow of the Big Bang where hints of interaction might linger. They track the motion of galaxies to see whether dark matter's influence weakens or strengthens with time. They measure how light from distant quasars is stretched as it travels through space, hoping to catch the faint fingerprints of dark energy's changing hand. So far, the results are inconclusive. The universe is generous with wonder but stingy with certainty. Still, the act of searching brings its own kind of beauty. Each new observation adds another note to the quiet score of understanding. Even if dark matter and dark energy never speak directly, the fact that we can sense both and feel their tug and push reminds us that we are part of their story. If you pause for a moment and think about it, every breath you take, every atom in your body, every photon that lights your eyes, all are balanced within this invisible conversation. The Earth orbits the Sun because of gravity shaped by both seen and unseen mass. The Milky Way drifts through the cosmic sea because of dark energy's gentle tide. Even the time it takes for your heartbeat to echo into silence exists inside this expanding fabric. In a sense, we are the only visible words in a dialogue far larger than ourselves. We are made of the small fraction of the universe that shines, but we live inside the volume ruled by the unseen. We are beings of light, suspended in the language of darkness. Perhaps, in the end, the distinction between dark matter and dark energy will blur. Perhaps they are not two mysteries but one, wearing different masks depending on where we look. Matter and energy, pull and push, gravity and expansion, each one a different accent in the same cosmic conversation. And when we finally understand it, we may realize that the universe has been speaking all along. Not loudly, not urgently, but softly, through gravity, through light, through the slow rhythm of expansion. A whisper that says, everything is connected, even the things you cannot see. For more than a century, Einstein's theory of general relativity has been the unshakable pillar of modern physics. It has guided spacecraft through the solar system, predicted the bending of starlight, and described the birth and death of stars. It works so well that most scientists hesitate to question it at all. Yet when we look out to the farthest galaxies and watch the universe accelerate under the influence of something we cannot see, a quiet question emerges. What if gravity itself isn't what we think it is? It's a delicate question, one that requires humility. Einstein's equations have passed every test in our neighbourhood of space: the orbit of Mercury, the timing of pulsars, the dance of black holes. But those tests cover only small patches of the cosmic stage. When it comes to the universe as a whole, we have only begun to measure the edges of its performance. What if, on the grandest scales, gravity behaves differently than it does nearby? What if the laws we've built our understanding upon are only approximations, like a melody that sounds perfect close up, but changes pitch when heard from a great distance? Some physicists have dared to explore that possibility. Instead of adding new ingredients to the universe, like dark matter or dark energy, they ask whether the recipe itself might be slightly off. Perhaps the equations of gravity bend under pressure, just as materials warp when stretched too far. Maybe space, at immense scales, plays by slightly different rules. One of the first attempts to explore this idea came from a scientist named Mordechai Milgram in the early 1980s. He noticed that the motions of stars in galaxies didn't fit Newton's or Einstein's predictions unless one assumed the presence of unseen mass. But instead of inventing dark matter, Milgram proposed a simpler possibility. What if gravity itself changed behaviour when it became very weak? His model, called modified Newtonian dynamics, or simply MUND, suggested that at low accelerations the pull of gravity doesn't fade as quickly as expected. It flattens out, explaining the steady rotation of galaxies without the need for invisible halos. It was an elegant idea, and for a while, it seemed to fit certain observations beautifully. The rotation curves of spiral galaxies followed the patterns Mond predicted. But as astronomers gathered more data from clusters of galaxies, from gravitational lensing, from the cosmic microwave background, it became clear that something was missing. Mond could describe the dance of stars within galaxies, but not the grand structure of the cosmos. It was like tuning an instrument that plays one song perfectly, but falls out of harmony with the orchestra. Still, the notion lingered. Perhaps gravity is not a single unchanging law, but a family of behaviours that shift with scale, time, or curvature. From this seed grew a whole garden of theories, each one a different attempt to explain cosmic acceleration without invoking dark energy. Some modified Einstein's equations directly, adding new terms that change how space expands. Others imagined that gravity could leak into hidden dimensions, like sound escaping through cracks in a wall. In one such idea, known as FR gravity, the geometry of space-time responds to more complex patterns of curvature, as though space has a subtle memory of its own stretching. In another, called brain-world cosmology, our entire universe is imagined as a four-dimensional sheet, like the surface of a soap bubble, floating within a higher dimensional space. Gravity, in this picture, can seep from one sheet to another, appearing weaker than it truly is. These ideas sound fantastical, but they are attempts to solve a very real puzzle: why the universe refuses to slow down. Physicists test these alternatives carefully, comparing their predictions against the precise maps of cosmic structure and light. So far, none have surpassed Einstein's theory. His equations continue to describe reality with quiet precision, their predictions matching what we observe with uncanny accuracy. But even that success carries mystery. Why should a theory built in 1915, a theory tested on planets and stars, still describe galaxies and the universe itself? Is it perfection or coincidence? Sometimes science advances not because we find a new truth, but because we dare to ask where the old truth might bend. Einstein himself once said, "To raise new questions, new possibilities, to regard old problems from a new angle, requires creative imagination. That spirit lives on in those who wonder whether the darkness we see is real, or a sign that we've misunderstood the light. After all, history offers many reminders that our perceptions can deceive us. Before Copernicus, the heavens seemed to circle Earth. Before Newton, motion seemed to require a constant push. Each time we've expanded our view, we've discovered that the rules are deeper and more subtle than we imagined. Maybe gravity too hides a deeper simplicity behind its apparent complexity. Some researchers even suspect that what we call dark energy could emerge naturally from the geometry of space, without invoking any new substance. In this view, the expansion of the universe is not driven by an extra ingredient, but by the way space-time itself responds to curvature on cosmic scales. It's as though the universe bends itself into motion, a kind of self-organizing expansion born from its own structure. Others imagine a hybrid truth, that both stories are correct, partly, that gravity does behave slightly differently at vast distances, and that the vacuum carries a small constant pressure. The cosmos might not choose between light and dark, theory and observation, but balance them, letting each reveal part of the truth. The conversation between these possibilities is ongoing, shaped by new observations from telescopes like Euclid and the Vera Rubin Observatory. These instruments will chart the motion of billions of galaxies, tracing how structure forms and how light bends as it travels through expanding space. The results may confirm Einstein once again, or gently correct him, showing that even his grand design has a hidden footnote. For now, the mystery remains. Gravity continues to pull, space continues to stretch, and we continue to wonder whether our understanding is complete, or just the first draft of a greater truth. When you think about it, there's something profoundly reassuring in this uncertainty. It means that the universe still has surprises left. It means that knowledge, like space itself, is expanding. And perhaps that's what makes science such a human endeavour, not its answers, but its willingness to listen to the unknown. So, when you look up at the night sky and imagine the gentle bending of starlight, remember, even the laws that describe that bending might one day evolve. Gravity could still be whispering secrets we haven't learned to translate, and whether we call them corrections, extensions, or entirely new ways of seeing, they will remind us of something simple and true. Every light has its limits, but curiosity never does. As the story of the cosmos unfolds, there comes a point when the questions we ask turn softly inward, not toward what began it all, but toward where it is going. We know now that space is stretching, that galaxies are drifting farther apart, and that the mysterious force of dark energy is gently accelerating this expansion. But how long can it last? What happens when the universe keeps moving outward, forever? And will there come a day when everything, light, matter, even memory, simply slips away into silence? Cosmologists have spent decades sketching the possibilities, each one a different ending to the same grand tale. They read the universe's future the way historians read ancient stone tablets, by the faint traces of motion carved into time itself. And though the scenarios vary, they all depend on the same invisible player: dark energy, the quiet pressure that fills the cosmos. If this mysterious energy stays constant, if it continues to push with the same steady hand it has today, then the expansion will go on forever. Galaxies will drift apart like lanterns carried on an endless sea. Their light will grow fainter and redder, stretched by the expanding fabric of space, until even neighbouring galaxies slip beyond view. Over billions of years, the night sky will grow empty. Only the stars of our local group, the Milky Way, Andromeda, and a few small companions, will remain bound together, forming a single island galaxy adrift in an ever-darkening void. Eventually, even those stars will die. The bright young suns will exhaust their fuel, becoming white dwarfs, neutron stars, or quiet black holes. Over unimaginable spans of time, these remnants will cool and fade, leaving behind a universe of cold dust and frozen light. Physicists call this scenario the heat death, not a fiery end, but an eternal winter. Energy will still exist, but spread so evenly that nothing new can happen. The cosmos will reach perfect balance, and in that perfection, all change will stop. It's a haunting image, but also a strangely peaceful one. The universe would not explode or collapse. It would simply drift into stillness, like a long exhale after an endless song. Some have called it the Big Freeze, a quiet fading of cosmic memory, where entropy, the tendency toward disorder, has finally won. But dark energy may not be constant. It might be shifting slowly, like a tide whose rhythm we can't yet measure. If its strength increases over time, even slightly, then the expansion will accelerate ever faster. The galaxies won't just drift apart, they'll be torn apart. Stars will slip from galaxies, planets will lose their orbits, and eventually even atoms themselves could be pulled apart by the stretching of space. This idea, dramatic and chilling, is known as the Big Rip. In this scenario, the universe ends not in fire or ice, but in isolation. The bonds that hold matter together, gravity, electromagnetism, even the strong force within atomic nuclei, would all be undone. It's a vision so extreme that it borders on the surreal, and yet, mathematically, it can't be ruled out. If dark energy's push grows stronger with time, the universe may unravel from the larger structures down to the smallest, leaving behind only a whisper of expansion, a final breath of space dissolving into itself. There is another possibility, one that turns everything back around. Some theories suggest that dark energy could reverse its sign, changing from a push to a pull. If that happens, the cosmic acceleration would slow, then stop, and finally reverse. Galaxies would begin to move toward each other again, drawn together by gravity's return. Over eons, the universe would contract instead of expand, its temperature rising as space shrinks. Stars might reignite, collisions would multiply, and the cosmos could end as it began. In a single point of infinite density, a big crunch. Perhaps that wouldn't be an ending at all. Some scientists have speculated that such a collapse could trigger another Big Bang, a kind of cosmic heartbeat, an eternal cycle of expansion and rebirth. The universe, in this vision, never truly dies. It breathes. Each age would be followed by another, with new galaxies, new stars, and maybe new forms of life. We don't yet know which of these futures awaits us. The clues lie scattered across the heavens, in the faint afterglow of the Big Bang and in the slow drift of galaxies. Missions like the Euclid telescope in orbit, the Vera Rubin Observatory in Chile, the Nancy Grace Roman Space Telescope above Earth, and the extremely large telescope rising in the Chilean desert, all are part of humanity's attempt to read that cosmic handwriting more clearly. They will measure how galaxies cluster, how light bends as it travels, how the rhythm of expansion changes over time. Somewhere in those patterns, we hope to find the signature of the universe's fate. And yet, perhaps the outcome is less important than the act of wondering. Every generation has looked up and seen the same stars, but every generation has imagined a slightly different story about what they mean. We might never witness the universe's final act, but we are part of its unfolding play. Our atoms, forged in ancient stars, will drift onward, recycled into whatever the next chapter demands. Whether the cosmos freezes, rips, or folds back in on itself, the ingredients of our being will remain, scattered, yes, but eternal. In the far future, if there are still observers somewhere, beings made of something we can barely imagine, they may look up and see a sky without galaxies, without constellations, perhaps without even the memory of light. They may find traces of an older cosmos in the faint background radiation, the last echo of our time. To them we would be ancient myths, stories whispered by particles, but in a way, that's what we already are. Echoes of stars arranged briefly into awareness, remembering the universe, remembering itself. There's a gentle humility in accepting that we may not be able to save the cosmos from fading, or explain every mystery before it does. The universe doesn't promise permanence, it offers participation. We are part of the great expansion, part of the conversation between gravity and light, between what shines and what doesn't. Even our questions, these quiet, trembling thoughts about beginnings and endings, are made of the same matter and energy that once lit the stars. So, as the galaxies drift away, as the night sky slowly empties across future millennia, there is no tragedy in it, only transformation. The universe, after all, has never stopped changing, and if it must one day dissolve into silence, then perhaps that silence will be like sleep, peaceful, unhurried, and full of the possibility of waking again. And if you're listening to this now, maybe that's the real comfort, that you are here, in this moment of cosmic motion, part of the brief era when the universe is bright, alive, and full of questions. Whatever lies ahead, freeze, rip, crunch, or something beyond imagination, we are part of it. We are made of its light, carried in its expansion, and destined to rest someday within its calm, eternal dark.